member. He was also a project scientist with CSIR Siri Pilani. He has published more than 55 papers in esteemed journals and conferences. His research interests include VLSI signal processing circuits and systems. CMOS-based analog digital and design also he is dealing with. He is currently an associate editor with the Journal of Circuit Systems and Computers, and he has been reviewer of reputed IEEE transactions such as IEEE transaction of very large scale integration, IEEE transaction of nanotechnologies, IEEE transaction of circuits and systems, IEEE transaction of computer design of integrated circuits and systems, and IEEE transaction of electron devices. So many reputed journals he is associated with, and he is the associate editor also. So now he'll present the topic on the Memristor Emulator. So please listen to him carefully, and after finishing his lecture, then only ask your question. And please be muted during the lecture session. You can start, sir.
Okay. Good afternoon, everybody. So I'm sorry for the delay. Today I'm going to give a talk on Memristor Emulator circuits and its application. So thank you for being here today as we explore an essential and existing topic in modern electronics, that is Memristor Emulator and neuromorphic applications mainly. So today we explore what is the Memristor and how we can emulate its behavior using practical circuits and its application in AI or instrumentation or neuromorphic places. And by the end of the talk, you will have a deeper understanding of how Memristor work and their fundamental properties, how to build and test the Memristor emulator, and the role of Memristor emulator in artificial intelligence and control systems. So practical applications we have also opportunity to see in these lectures. So these are the scope of my presentations. So initially I will highlight the importance of current mode building blocks and its usefulness in analog signal processing circuits and Memristor emulator. Then we will discuss the few analog building blocks. So analog building blocks such as current conveyor, OTA, these are the most important and fundamental analog building blocks. Then thereafter, what is Memristors, how it is different from Memristor device and its properties. And Memristor emulator design using current mode building blocks and simulation results and experimental results. And there afterwards, I will show the few applications, then conclusions and differences. So now current mode circuits are circuits are divided further into two types. One is the voltage mode circuits and another one is current mode circuits. So active variables is a voltage preference in the current in a voltage mode circuit, and current mode circuits active variables is a current in preference to voltage. So these are the few differences between voltage mode circuits and current mode circuits. So these are the few advantages. So current mode circuit signals are normally represented by currents. So we saw after the simulations and experimentals, so the speed is high in compared to voltage mode circuits. So less power consumptions, higher signal bandwidth, large dynamic range, and less supply voltage and greater linearity. These are the few advantages over the voltage mode circuit in case of current mode circuits. So now, so this analog building blocks, the second generation current conveyors and OTA is the most important building blocks in the current mode circuits. So the CCTA is the combination of this double C2 and OTA. So that is called current control transconductance amplifier. So and thereafter also there is differential voltage current conveyors transconductance amplifier. See here we will use DVCCTA. So here is the combination of transconductance amplifier and DVCCTA. So these 3-4 blocks is important for the current mode circuits. So then various applications of the current mode circuits are in oscillators, filters, amplifiers, Memristor emulators, and semi triggers. These are the few analog signal processing circuits we use in the Memristor Emulator circuits. So now the second generation current conveyor is shown here. So this is the symbolic representation of double C2. So here double C2 plus and port relationship is shown here. Here IY equal to 0 and Vx equal to Vy and Iz equal to Ix. And the internal structure of double C2 is also shown here. So here, if you see this Q5, Q6 is a one current mirror, Q7 and Q8 is the another current mirror, and this Q1, Q2, Q3, Q4 is a translinear loop. So here, if the VBE across the Q1 and VBE across the Q2 is equal, so Vx equal to Vy. And then correspondingly, this Iz equal to Ix, how this IC2 current is transferring here to the Q6 terminal, and IC4 transfer current is transferring to here Q8 terminal. So here you can see from this diagram that Iz equal to Ix and Iy equal to 0. So this is about the second generation current conveyors. Now this is second generation current conveyor negative. So here we can see Iy equal to 0, Vx equal to Vy, and Iz equal to minus Ix. So in this case, the structure, if you see the double C2 plus and double C2 minus, so both are same, only phase change. We have cut it in the one terminal and connected back to back connection, so that so Iz equal to Ix minus Ix, and others are same. Now this is the commercial available second generation current conveyor, that is AD84AN. So here this properties of this circuit same, which I already discussed just now, and practical view means the ideal ones is how much difference to practical ones. So here at the Y terminal, RYCY is the parasitics, and X terminals have another parasitics, and RZCZ is another parasitics available at the different ports. So this AD84AN is available in the market. So this is its pin diagram. So here 1 and 8 is not used, 2 is a inverting, 3 is a non-inverting, 4 is a plus V, and 6 is the output, and 7 is the minus V. So this IC you can purchase from the market. Now this is the important one, current mode building blocks. So this is operational transconductance amplifier. So this circuit symbol are shown here, and this is the port relationship. So here IP equal to 0, IN equal to 0, and I0 equal to GM VP minus VN. So this is the port relationship of this one. So here I0 equal to GM VP minus VN, and GM equal to K under root 2 VB minus VS minus 2 VTH. So this is actually MOS based OTA. So this MOS based OTA and BJT based OTA having some basics difference. So here you can see that GM is proportional to the I0 with I0 output current, and VP minus VN. So I is proportional to differential voltage. GM is the actually constant. This commercially available CA3080 is shown here. So this is I0 equal to GM VP minus VN, and GM equal to IB upon 2 VT. So here GM is proportional to biasing current. So in this case, voltage is applied for the controlling the transconductance, but here we are applying current, biasing current IB to change the transconductance of the OTA, and VT is the thermal voltage. So this CA3080 is available in the market. So here 2 and 3 is inverting and non-inverting, 6 is the output, and 4, 7 is the biasing voltage is applied to this circuit. Now this is the current conveyor transconductance amplifier. So here you can see that this portion is a current conveyor. So Z1, Z2, Z3 is nothing, only is showing the current mirror, and this portion is a OTA based OTA circuit, transconductance amplifier. So the CCT is nothing, it is a combination of current conveyor and transconductance amplifier. So Now port relationship, you can see Iy equal to 0, Vx equal to Vy, Iz equal to Ix, and I0 equal to plus minus Gm Vz. And Gm, you can find this Gm equal to K by 2 V1 minus Vss minus 2 Vth. So advantage here in this circuit, we will get the advantage of both CC2 and OTA. It is a combination of CC2 and OTA. So we will get the advantage of both. This is the this CCTA is not available in the market. So we want to do the experiment of CCTA based circuit. So for that we took this 2AD844, which is nothing, which is CC2, and CA3080 is another OTA. So that proposed circuit, that circuit has been designed using CC2 and OTA. This is called CCTA. This is the practical view with CCTA. Another block is DVCCTA. DVCCTA is nothing. This is DVCC, differential voltage current conveyor, which is cascade connections of DVCC and OTA. Transconductance gain is electronically tuned by an external voltage. So it is used. It is called transconductance, because in the transconductance amplifier we also change the transconductance. So here this Gm can be defined as KVC minus VSS by 2 minus VT. So this is MOS based DVCC TA. Here this portion, half portion is DVCC and half portion is transconductance amplifier. This was discussed, that was the current mode analog building block fundamentals. Now I'm moving to the memristor circuit. So many lectures you have already heard from Professor Kang. So that I want to brush up only. So this memristor is theorized by 1971 Leon Chua. So you can see that is PI relations dV equal to RDI, and I and phi is d phi equal to LDI, and V and Q is relation dQ is equal to C dt. So this phi and Q is the missing link. Phi and Q is the missing link. So from this graph you can see that this current and voltage graph is in inductor case is like circuit, capacitor, and this one is circle, but memristors graph is pinch hysteresis loops, that it should be pinched at a center. So the symbol is shown here, and d phi equal to mdq and dv equal to rdi in case of resistor. So memristor is a symbol is shown here. So memristor is a non-linear memory with resistor and having unique behavior and characteristics. It is a two-terminal device. It is, just wait. So it is two-terminal device. It was an element that changed its resistance depending upon how much charge flowed through it. And its resistance depends on the physical history of the circuit, or if we made using MOS circuits, and its unit is ohm. Symbol is shown here. So based on the memristor relations, there are two types. One is a charge control memristor and another one is a flux control memristor. The voltage across a charge control memristor is given by Vt equal to mqt it, and hence mq equal to d phi q upon dq. Then current is of flux control memristor is given by it equal to wqt vt and w phi equal to dq phi upon dq. So these are the basics equations for the charge control memristors and flux control memristor. So the fingerprints of memristor is the pinch hysteresis loop in the current voltage plane is driven by bipolar periodic signals. So the low area of hysteresis loop should be decreased monotonically when excitance frequency is increased, or vice versa. The physical pinch hysteresis loop shrinks to a single valued functions when frequency tends to infinity. It acts like a linear resistance at high frequency. These are the unique properties. So it is called fingerprints of memristor. Memristors also exhibit non-volatile property. So memristor of emulators remains unaltered when no input signal is applied. So these are the few important properties of the memristors, and that is called fingerprints of memristor. So these are the few advantages. So memristors are compatible with interface of CMOS. It does not use power when inactive. It not requires any power if it is in inactive mode. It consumes less power for generating less heats. It has very high storage density as well as switching speeds. It has capability to memorize the flow of charge in a set time. So now why memristor? So this is the important one. So emulators are circuits to mimic the characteristics of memristors. So nano-scale memristors have high voltage fabrication costs and technical difficulty in productions. So memristor emulator is required. So memristor is something different, but emulator is something different. In emulator case, we copy all the properties of memristors using CMOS. So the compatible with CMOS technology, it is simple to develop precise spice macro models. The dynamic behavior of memristor emulators can be modified as to explore their design issues and potential applications. Now, there was the discussion about memristors and what was the fingerprints and what is the advantage and etc. Now, first memristors our group has designed, so that is called CCTA based memristors. So here we have used CCTA block. So both grounding and floating is possible in this case and configured in incremental and decremental mode. Meaning of incremental and decremental mode means here current direction will reverse. So it can operate up to 1 megahertz. So now this is the actual circuit diagram. Now we'll see what is the derivations, how we'll get it. So we know that property of CCTA we already discussed in the previous slides. So if you derive the voltage at this port 1, input voltage can be written as V in T equal to I in T into R1 plus Vx. Okay, so now using the port relation, this is the port relationship of this block. So port relationship means what is the value Vx we have applied, that will be copied to Vy. Even Vy voltage is equal to Vx and I0 equal to GMVZ2. This is the port relationship of CCTA. So where what is the Vx? Vx equal to Vy equal to I0 and I0 R2. So what is the I2? Here we have 2 plus 2k V1 plus VSS minus VT. This is the value of GM, VZ2 and R2. So we receive this one. So now on substituting we get it VZ2 equal to I into T R3 and K equal to mu x CXW by L and V1 equal to QCT by C. So after manipulating this equation or after analyzing this equations, we got MQCT equal to V in T upon I in T, which is equal to R1 plus minus 2K R2 R3 VSS minus VT plus minus 2K QCT upon C R2 R3. This is the memristor equations. Now, floating memristor will be obtained at port 1 and port 2. Here and here you will get floating memristor and grounded is port 1 and ground 2 or Z2 terminal. So this is the memristor equations we have received from after that. This is a theoretical analysis of this CCTA based memristor. Now, so here we can see that this equations is shown here also. Memristor equations. So here this is the time varying part, this is time invariant part. So everything is constant here. So assuming input voltage is V in T equal to AM sine omega T. So we are assuming this one. So that voltage is applied to the memristor, input voltage of this circuit. So Average input current can be found by substituting time varying part is 0. Okay, so I in T equal to V in T upon R1 plus minus 2K R2 R3 VSS minus VT. And we know that charge equal to integration of I in T. So as a result, charge is given by QCT equal to AM upon omega R1 plus minus 2K R2 R3 VSS minus VT into cos omega T pi. So on substituting this value in this equation, so we received QCT equal to V in T upon I in T equal to R1 plus minus 2K R2 R3 VSS minus VT. This is the linear time invariant part plus minus 2K R2 R3 AM divided by omega C R1 plus minus 2K R2 R3 VSS minus VT into cos omega T minus pi. This is the linear time varying part. Okay, so here you can see the linear time variancy, and also you can see from the fingerprint we know that when omega is high means this term will be 0, so only linear part will be available. So high frequency it behaves like a linear resistance or resistance. So this is the nothing. This is the non-ideality analysis at the circuit which we are using, that is the CCTA. So from that we know that the IY equal to 0, Vx equal to beta Vy. This beta is a non-linearity available at the port. Ideally we get Vx equal to Vy, but normally in the practical case Vx is 0.99 times Vy. So these are the non-ideality. Iji equal to alpha I Ix, I0 equal to gamma gm Vz, and Iji equal to mu x Iji, mu Iji, alpha Iji. These are the non-ideality. So that value we put on the similar equations, we get different types of two equations: grounded for incremental and decremental, floating for incremental and decremental equations. So these are the simulation results. In the ORCID, we have applied the input signal sinusoidal wave correspondingly memristor we have achieved for this is the incremental and this is the decremental case. So this is for the omega C is also another property of the memristor. So we have received this type of incremental and decrementals. So you can see that this constant same value is appearing. Now memristor behaves at another increase or decrease. We can see that this different value of capacitor. So you can see that 0.2 and 0.05. So it is shrinking. So this is then another important fingerprints verification of the memristor. Now this is the practical implementation of emulator. So here we have in the laboratory we have designed and fabricated this PCB design of memristor emulator using AD844 and CA3080, and this is the macro model's structure. So we have done this experiment in the laboratory. So using this component value R1 R2 is equal to 10 kilo ohm, R2 R4, and these are the voltage we have applied. So we received this C equal to 10 nanofarad. We received 5.16 kilohertz. It behaves like a memristor, and at 30.4 kilohertz at C equal to 10 picofarad we received this. So you can see here this is shrinking. The pinch resistance to is shrinking. Now next is memristor emulator 2, that is DVCC TA based structure. So here we have used 1 DVCC TA and 3 resistors and 1 capacitor. So also it behaves like a non-volatile property, and both incremental and decremental it will work and operate up to 1 megahertz. So now this is the circuit structure. So here you can see V in equal to I in T R in plus Vx. So at O terminals we receive this circuits O terminals which is act as multipliers, and output Vx equal to minus plus K VCC minus VSS upon 2 minus VT INT R1 and R2. So using these equations we will receive the equivalent memristor equations, that is shown here, equation 3. R in equal to minus plus K minus VSS by 2 minus VT R1 R2 minus plus K R1 R2 QC QT upon 2 C1. So this is again this time varying part, and this is time invariant part. After the analysis of CMOS memristor emulator circuit in decremental configuration has performed using 0.25 micrometer TSMC technology, when voltage is Vm equal to 200 millivolt, Rin equal to 6 kilo ohm, R1 equal to 400 ohm, and R2 equal to 2.2 kilo ohm. So for C1 equal to 1 microfarad, this is the simulation result, and C1 equal to 100 nanofarad, this is the simulation result. Now simulation is performed different frequency when omega C1 equal to constant. So this you can see omega C is constant. So all the loop coincide and area under pinch hysteresis loop remains same. Both the case you can see. Now this is showing the pulse of 1 volt having width of 1 microsecond and time period of 1 millisecond is applied, considering the f equal to 50 kilohertz and C1 equal to 0.5 nanofarad. So you can see that this is the non-volatile property. So here is applied one pulse, but here no any pulse is applied, so this value is retained. So this shows the non-volatile property of the memristor in incremental technology, and this is then the decremental technology or decremental mode, we can say. Now we have done the experimental result using the DVCC TA base, but DVCC is not available in the market. So we have purchased few CC2 and AD844. Again, macro model circuit is designed in the laboratory, and we have done the experiment. This experiment is frequency at 50 kilohertz and this frequency at 100 kilohertz. Now, third one is a flux control memristor emulator. Here we used two blocks. One is a CC2 and another is a OTA. So it again configures in incremental and decremental mode, and it can operate up to 25 megahertz. Routine analysis yields Vx equal to Vy from this circuit. You can see that Vx equal to Vy equal to V in, because here both the voltage is apply input voltage, and Vz Vb equal to phi in upon Rc, phi in upon Vz and Vb same. So here equations will get phi in upon Rc. So I in equal to K upon under 2 phi in upon Rc minus Vss minus 2 Vth into V in. So memdactance is found here. So memdactance of proposed this circuit is incremental configuration is shown here. So it is reverse of memdistance. So that is I in upon V in, which is equal to minus K upon under root 2 VSS plus 2 VTH plus K phi in under root 2 RC. So the frequency response analysis of memristor circuit is this one. So this circuit, this portion is a time invariant part, and this is the time varying part. So phi equal to AM divided by 2 pi FRC VSS plus 2 VTH. So memdactance considering the non-ideality is this one. So non-ideality means that Vx equal to Vy, so Vx equal to beta times Vy. So that considered, we have considering that we will put here. So we will get these equations. Simulations results. Here we have used for 0.8 micrometer GPDK parameters, which is available in the cadence tools. Supply voltage is 1.2 volt. Considering the R equal to 40 kilohertz and C equal to 160 picofarad to 0.5 picofarad, we have varied it, and we get this memdistance diagram. So that 4 kilohertz pinch hysteresis you can see here, and 500 kilohertz you can see red one, and 600 kilohertz is blue one. So similarly 800 kilohertz, 1 megahertz and 1.2 megahertz. Here the capacitor value reduced in order to hold the hysteresis loop at high frequency is shown here. C 2 picofarads, 0.98 picofarads, and C equal to 0.5 picofarad. So loop area decreases with increasing the frequencies. So that is the main fingerprints of memristor emulator. Different value of capacitors maintaining constant frequency. So this is the graph of 12 picofarad to 30 picofarad. Here 5 picofarad to 15 picofarad. So lobe area decreases with increment of capacitor value. Keeping the product of omega c constants. So here if omega and c is constant, so all hysteresis curve coincide and looks alike, and phi remains unaltered both the cases. Temperature effects on hysteresis loop of 1 megahertz we have analyzed it. This is the different temperatures graphs is shown here. Here various temperature and process corners we have done it, and different process corners we have done it here. So less current flow in SS process corners, while more current flow in case of FF. So this is another one non-volatile property of this circuit. So here this is the incremental configuration and this is the decremental configuration. So pulse sense is applied like this. So this portion is a non-volatile, means in between this there is no any pulse, and that value is retained by this memductance. So memductance is non-volatile and its variation is negligible during the non-pulse periods. So same memductance value is preserved. So we have also facilities in the cadence. So Monte Carlo analysis, so examine at the mismatch at 1 megahertz and done for 150 runs, and considering random sampling methods for mismatch and process statistical variations, this one, then still operation is within the acceptable limit. This is the pre-post layout simulation of the memristors, DVCC TA based memristors, or CC2 or OTA based memristors. So here you can see the pre and post simulation is almost more matched. So to check the effect of parasitics on the overall performance, we have done it, and layout area is 75 microfarad to cross to 70 microfarads for this case. We have done the experiments. AD844 we purchased from the market, and CA3080 is purchased from the market. The supply voltage is shown here, and frequency we have tested at this frequency. So F equal to 4 kilohertz we received this one, and F equal to 800 kilohertz we received this type of pinch hysteresis, clear showing that the pinch hysteresis is the property of the memristors. This is the experimental result of 1 megahertz, and this is the experimental result of 1.4 megahertz. So distortion have been observed on further increasing the frequency. Loop becomes deformated, resulting in a asymmetrical behavior. Loop becomes narrower when frequency is increased. Now next is charge control memristor emulator. So here CC2 and CCTA is used. So port relationship is shown here. So these are port relations I already discussed, so I'm not giving much more time in this case. So routine analysis derivations is similar, which I many times have discussed. PA equal to this one, BB equal to this, VAB, this point to this point. So memristance of this circuit is shown here. So MABQ equal to R1 plus 2 plus minus K R2 R3 VSS by 2 plus BT minus plus K R2 R3 QCT upon 2C. So this is the memristance we have received from this circuit. So here frequency analysis of done it. So this equations, memristance equation is shown equation 7. So this is the time invariant part, and this is time varying part. So for this phi equal to, we have calculated from this phi equal to T upon tau. So we have received this phi. So this is the ratio of time varying to linear time invariant part. Time varying to linear time invariant part. That is also somewhere required. So we have done it. Simulation result is shown here. So capacitor value has to be reduced for holding the hysteresis loop at high frequency. Here all hysteresis loop coincide and look alike. Omega c remains constant. So we have also done the simulation of the circuit. Here low area decreases with incremental of capacitor value of both the case. Different value of capacitors maintaining constant frequencies. Non-volatile property. This is the non-volatile property of incremental configuration. This is the non-volatile property of decremental configurations. We have done the experiment using CA3080 and 8844 of this circuit. So 100 kilohertz, we receive this type of pinch stress loop. And here is the comparison with macro model. Macro model means simulation based and experimental circuits that data took from CSB, and we have done it. We can see the comparisons at 100 kilohertz with parameter also on here. So now next is applications of memristors. So memristors are applicable for RLC circuits and analog filter applications. Memristors used in nonlinear circuit like CHUA, because memristor is nonlinear, so we can replace the diode. Low power applications also, and it's also used in storing analog signal processing circuit like semi-trigger circuits. Memristors are used in digital memory and logic circuits. Memories are used in neural networks and as well as in neuromorphic circuits. These are the few important memristors applications. Here you can see this memristor is one application, singles. This is the graph as singles. Singles is black one, parallels is red one, and series, if you show in series, then series is this one red. So this is the, if I connect the memristors, so how looks like the graph is shown here. Now this is the analog filter. So we know that RC filters. So RC filters, in place of R, we put a memristors, and we this is the cutoff frequencies graph or filter frequency and gain graph. So you can see that this frequency is changing at this place. Cutoff frequency is changing when the frequency is modified. Cutoff frequency of demand based filters can be modified accordingly. Now memristors as a amplitude modulation for FM signals. So here this is the memristors, and this is the op-amp circuits, inverting circuits. So here FM signal is applied, V in is op-amp, so BFM is output, we have received it, and then again demodulated. So here you can see the FM signal, so correspondingly the FM amplitude modulated signal is shown here. So here low frequency, low amplitude we are received, and here high frequency, high amplitude signal is received. Now this another applications, important applications. So this is the memristor based CHUA circuit. So diode CHUA you already heard about it, that one. So in place of diode we replace this memristors. So this is the theoretical equations. Now we have done this simulation also in the laboratory. So we have this is the chaotic output obtained at BC1, and this is the BC2, different memristors based chaotic oscillator. This is the important informations for transmitter and receiver communications. This is the 5D quantity. So this is the different attractors at obtained at IL1 and IL2. We can also use these memristors in AI. So ability to solve the problems, ability to act powerfully, ability to act like human. Human means neuromorphic. So memristors can create super fast memory chip with more data in less energy consumption. This is the important one. We are working on that one. Applications: gate allocations for plane while landing, ticket pricing determination, robots. These are the research is going on, and there are the various applications of memristors in the AI also. Now these are the different gate we can design it using the memristors, OR gate, AND gate. So people are working on this area also. Another one is an important applications is memristor for spiking generations. So here this is the available in the literature, that leaky integrated fire. So this is the current injection circuit, and this is the semi-trigger portions, reset or leaking integrated circuit. So here this is the current mirror, integrator or semi-trigger. This is the MIF. So this LIF we can use this using MRE. MRE means memristor. So we have used here memristor. So it is called memristors integrated fire neurons. And here, but property of this LIF is converted to MIF by minimizing the circuit structure, and few structures comes for the memristors also in these neurons. This is the MIF. So MIF, this MIF, MRE is this one is the our design Memristor emulator. So we include in the LIF this circuit, so that becomes a new circuits, and we receive the different types of properties of the memristors in this case. Now this one is chip macro graph image, so fabricated at Unitech Microelectronics Corporation, Belgium. So layout area is 745.52 micrometer square. Die size is 1499.96 and cross 1499.96 micrometer. 44 pins is available. So here is memristor emulators we have designed and we have fabricated, and these are the ADC. Now, after receiving the chip, so we have done this experimental results are fabricated Memristor emulator chip. So we received clear these three different types of pinches do. So a sinusoidal signal is applied at the input of the test chip with amplitude of 1.2 volt. The chip is tested for different frequency, you can see, and the input signal frequency is taken at 5, 10, and 50 kilohertz. So transient response of test chip at 10 megahertz, PHL of 10 at 5 megahertz, PHL of 10 at 10 megahertz, and PHL of 10 at 50 megahertz. So these are the first time we have fabricated this chip from the IMEC Belgium, and we received the different output. Here the experimental result with theoretical one, simulation one is shown here. So we took the graph from CSB and we have done it. Comparison with no memristor, Professor Kang is already discussed. We have also compared with no memristors. Maximum current is 1 micrometer, 1 milliampere. Here our memristor is greater than 1.5 millimeter. Set reset is this one. So our set reset is this one. Electroforming, here forming free, and maximum operating frequency is 1 kilowatt. But this is the property of 50 kilowatt is our memristors operating frequency. Remember, here is the MIF circuits, so which I already discussed. So power consumption is 19.6 macrowatts, energy is back 196 picojoules, and 443 pico. What is the static powers? So these are the few parameters we have used it. Simulation result of MIF neurons is shown here. So these are the simulation results of this MIF neurons. This is also the simulation results of MIF neurons. These are the simulation results. So this is showing the static voltage versus spike neurons. Electronic neuron circuit comparisons. So these are the compared with available literature. So Morse counts is very less in our case. Energy spike is 196. Static power is this one. Refractory period is available, but in memory computation available. Others are not reported any that memory computing. Here this MIF is fully neuromorphic framework for pattern recognition. So we have also designed the circuits of pattern to be recognized are pixels representing 4 randomly chosen letters. Each letter is assigned different columns where they are arranged as per their weights and resistance matrix. Each cell is pixels denoted memristor static voltage embedded within the MIF. Off state green pixels, on state blue pixels. Okay, so pattern C, its weight and matrix is this is the pattern C, and for B, this one is pattern F, and pattern I is shown here, and D is the P is shown in the figure D. Its weight matrix is shown here. So here timing is T equal to 0.05 milliseconds, T equal to 0.5 milliseconds, T equal to 0.95 milliseconds, T equal to 1.4 milliseconds. This is the MIF neuron crossbar structures, that circuit we have used, and we have used here. We can see this, the output is connected, and we received out 1 equal to C type pattern, and F type out, then I type pattern, and then 4 is P type pattern. This is the layout of MIF neuron crossbar. Here 850.4 8 micrometer, and here 391.76 micrometer. Software we have used for this 180 nanometer CMOS. Total neurons is 48. Power supply plus minus 180 volt, and the out area is shown here. This is the simulation result of the circuits which we have done it. We have designed, and these are the simulations shown here. This is also simulations result. This successfully learning as per train pattern. We have trained it and can be easily validated through inspections and output voltage spikes at the respective output mode terminal, out 1, out 2, which is shown in this slide. This one. And further pre and post layout simulation output of C is shown out. This one is. This is also there arise no significant variation in the amplitude and output specs in each of the pattern, thus robust to process variations. This is also the Monte Carlo analysis. We have done it, and we received the histogram plot of Monte Carlo graph, and variation of state variable with temperatures is shown here. So energy consumptions for this pattern C, we have received C equal to 4.807 picojoule, and pattern F equal to 5.13 picojoule, a pattern I 5.411 picojoule, a pattern P equal to 5.673 picojoule. Thus, the average energy equal consumption is 5.25 picojoule, which is very good. So these are the references we have used while I have given the presentations. Thank you. Now, questions are invited. Am I audible to?
Question you can ask.
Yes.
Am I audible? Hello?
Yes, yes.
Requesting attendees to ask the question from the professor. If you have any doubt. There is a question, sir, in the chat box. Is there any relationship between memristor, mem capacitor, and mem inductor?
Actually, all three are mem element. But physically, memristor is available. No memristor, but mem capacitor and mem inductor is not reported till. Okay. Next.
Good afternoon, sir.
Yes.
I have a question. In one of the slides, you've mentioned about doing the Monte Carlo analysis in cadence.
Yes, yes.
Since this is an emulator circuit, there are CMOS components, so we are able to do Monte Carlo analysis without any CMOS elements, but only using memristor. Is it possible to do the Monte Carlo analysis? Because I tried it, and then we are not getting the options because there is no GPDK for the memristor. So is there any other possibility to do Monte Carlo analysis with just memristor element being used?
No, you are working on device or circuit?
I'm working on both, sir. I'm making a device and I'm also trying to do an application using circuits.
The circuit you have an option now, Monte Carlo analysis.
Yes, sir, but then we are not able to do any process variation because there is no memristor element in cadence, and we have to import the Verilog A code and then do it. Because we are importing the Verilog A code, it's a bit hard to do the
No,
Monte Carlo.
that way you cannot do. You have to first design the circuits in the CMOS. So then you can do it probably. If you face any problems related this one, so you can write an email. So I will guide you.
Okay, sir. Thank you.
Sir, someone is asking about how to know whether a memristor emulator is grounded or floating.
So you can know if two port is coming at two terminals. If you know any in between is grounded, then that you can understand that memristor is floating. And if any terminal is grounded, that you will able to understand that is grounded.
Sir, good morning, sir. Sir, in the CCTA, if you can show now how to know it. In your slides, when CCTA Memristor Emulator was there, in which you have shown.
Okay, I'm going.
Yes.
Yes.
Yes, sir. In this one, sir, how to know whether it's like grounded or floating? This by looking at this.
Actually, exactly, it is not like that. So just I'm showing one what is meaning of grounded and just wait. One is clearly showing the this is one the floating exactly. This terminal, because this current here is coming and this current is equal to this current INT. This is the floating.
So in slide number 29. Sir, yes, sir. So here for 5.16 kilohertz, so the like this PHL, this is like not at the origin, and for like higher frequency, it is I think it's at the origin. Sir, may I know the reason why is it's happening
Actually,
like this?
this is nothing. Both are in the original, but this is the effect of non-ideal effect or parasitic node effect only. Okay, theoretically both are same, but these effects comes from non-ideality of the IC integrated circuit.
Slide number 34.
Yes.
So in this one, sir, from which port, sir, we are taking the voltage and current to like to show this non-volatile nature?
At the capacitor.
The voltage and current both we have to take from the capacitor.
Voltage only need to take. Voltage, capacitor. So you will get the non-volatile.
Okay, sir, and current from the input port only.
Yeah.
Okay, sir. And so slide number 67. So here, this CM capacitor, sir, it is connected to. Sir, where it is connected in this Memristor emulator?
CM is not actually memristor emulator is only this portion actually MRE.
Yes, sir. So this VP and VN.
So this is only,
this
actually this is if you this is the symbol of this memristor emulator we have put it here. VP VN is this one. VP VN is this one. VP VN. Okay.
Yes, sir.
So
yes,
we
sir.
have only we want to convert into LIF to MIF only.
Yes, sir. So for converting, sir, this input terminals of this Memristor emulator, that P terminal and N terminal, that is VP and VN, these are connected here, like it is connected here in this one.
You
But
can
this,
you can see VP is here and VP is connected to ground. Okay.
yes, sir.
Then N is the input, so N is the input in this way.
Okay, from the attendees, if you have any doubt regarding or you want to know further about this course, so you can ask mail to the professor personally. By giving this Gyan course ID, he will entertain
If
you
you
and
face
he will
any
solve it.
problem related to this one, so you can email to me so that I can elaborate more if required. Okay.
Thank you, sir. Yes.
Cool. So next class will start at, sir, when next class will start?
3:30.
3:30.
Hmm.
It is scheduled at 3 p.m. sir, actually.
No problem. 3:30 or 30 minutes late. So because in the
Okay,
first.
okay.
Mhm.
Okay. The next tutorial, that is tutorial 1 class, will be start at 3:30 p.m. So kindly join at that time. So you can end the meeting, sir.
Okay.
Done, sir. I ISM वाला पहले.